All right, so you're ready to take a deep dive with us today into the world of logic-based AI.
That's good.
That's what we're doing today, and we're going to get into some of the philosophy behind AI and using as our guide the Stanford Encyclopedia of Philosophy.
Excellent.
So we're going to talk about all sorts of things today about how to, logic and AI are intertwined, and can we really teach computers common sense?
Yes.
How do robots predict what will happen next?
Yeah.
And what does a dead turkey have to do with any of this?
Oh, I love the dead turkey problem.
Exactly. It's a classic.
It's a classic.
That's a good one.
So first of all, let's just lay the groundwork a little bit about computer science, logic, AI logic. How is logic used in AI compared to philosophical logic?
Right. Well, so the first thing to keep in mind, I think, is that computer science logic and AI are all about building working systems.
And philosophical logic is more about theoretical models. And so there's going to be a little bit of a difference between the two. But early AI pioneers like John McCarthy were very influenced by philosophical logic.
Right.
And in fact, in his seminal 1969 paper, 35 out of 58 references were from philosophical logic.
Wow.
That's pretty telling.
It is.
So, yeah, there's a lot of overlap there.
Yeah, there's a definite connection there. And speaking of John McCarthy, this article really gets into his ambitious goal of formalizing common sense reasoning.
Right.
And, it gives all these examples about how we can understand stories.
Yeah.
We diagnose problems. We can navigate to the airport. All this stuff that we just do without even thinking about it.
Yeah. It's like second nature to us.
Right.
But it's incredibly hard to formalize.
Right.
And think about why that is. I mean, why is common sense so difficult to formalize?
I know. It's true.
Why?
Is it really logical?
Why? Exactly.
Is it really illogical?
I mean, I guess that's the question.
Right.
Yeah. And we are making progress in some areas of logic-based AI, like in robot planning and multi-agent systems, those kinds of things.
Yeah, for sure. For sure. But then we get into this area of non-monotonic logic.
Yes.
Which I think is really fascinating.
Yeah.
And it basically says that traditional logic, which is designed for math, it isn't really enough for AI because AI has to deal with this idea that as you learn more information, your conclusions might change.
Exactly.
It's not just a stacking of facts.
It's not just a stacking of facts. It's this dynamic process.
Right.
And it's really what makes AI so interesting, I think.
Yeah. Well, and it gives the example in here, and I love this example. You're planning to go to the airport. You don't really worry about meteors hitting the Earth.
Yeah.
You just assume that's not going to happen.
Right. You just assume that everything's going to be fine.
Everything's going to be copacetic.
Yeah.
But that's non-monotonic reasoning.
Exactly. It is. And the formal side of that is that, new information can change your conclusions.
Right.
And that's very different from classical logic, where you just keep adding more and more information and it just builds on itself.
Right.
So, yeah, it's a very different approach.
So this article talks about 3 early approaches to non-monotonic logic.
Yes.
Circumscription, modal approaches, and default logic.
Yes.
And they all sort of try to tackle this challenge of how to deal with incomplete information.
Right. And one of the problems they all face is this problem of circularity.
Yes.
How do you define a proof when what you can prove depends on what you can't prove?
Right.
That's the problem.
Yeah, so it's kind of like,
It's a tricky one.
Yeah, so that's like the classic definition of circular reasoning.
Exactly.
Right.
And it's something that AI researchers have been struggling with for decades.
Okay, so that's non-monotonic logic.
Yes.
And we're going to get into the Yale shooting problem next.
Ooh, the dead turkey.
But first, we're going to take a little break.
Okay.
And we'll be right back.
Sounds good.
Yeah.
And it actually leads to all these other problems that kind of came after that.
Right.
The qualification problem.
Yeah.
The ramification problem.
Yes.
So all these kinds of interesting things pop out of the fact that we can't model the world perfectly.
Yeah, and they all are sort of related to this idea of inertia.
Yes.
That we were talking about before, and the frame problem.
Yeah.
So the qualification problem deals with the fact that most common sense rules have a huge number of exceptions.
Right.
Like we were saying about the birds can fly.
Yeah.
Well, but there's penguins, there's ostriches, there's birds with broken wings.
Exactly.
Yeah.
So there's all these exceptions. And if
Yeah.
you try and list all the exceptions in your logical system, it becomes overwhelmingly complex.
Right. You'd have to have like this infinite list of exceptions.
Right.
So how do you...
And that's where non-monotonic logic comes in again. It says, okay, we have a default rule.
Yeah.
And then we can just say, unless there's a reason to believe otherwise, we're going to assume this is true.
So it's like... Yeah.
So it's like, okay, birds typically fly unless there's a reason not to.
Unless it's a penguin.
Exactly.
So that's the qualification problem. But what about this ramification problem?
Yeah.
This one always sounded a little bit more,
Explosive.
yeah,
Yeah.
because it deals with like all of the ripple effects of actions.
Every action has consequences,
Right.
both intended and unintended.
Right, and it's like this domino effect.
Yes.
Where one thing leads to another and leads to another.
And capturing all those ramifications in a logical system
Oh my gosh.
can be incredibly difficult.
I know.
I mean, imagine trying to list every single consequence of walking into a room.
Well, you're closing now in the room. The air pressure changes slightly. You track in pollen on your shoes. It's like...
Exactly.
Yeah.
And do we need to specify every single one of those consequences?
I know, it's like...
In our logical system, how do we know which ones are relevant, which ones can be ignored? It's a nightmare for an AI programmer.
Yeah, it really is.
But there are some strategies.
Yeah.
One is to use causal theories
Okay.
to focus on the most relevant ramifications.
Right.
You know, those that are directly caused by the action.
Okay.
Other approaches use non-monotonic logic, again,
Right.
to establish default assumptions about what's going to change and what's going to stay the same.
So you're just saying, like, you have to kind of teach the AI system to be selective.
Yes.
About which consequences it even considers.
You've got it.
Because otherwise it would just be overwhelmed.
Yeah, exactly.
Right.
You'd just be overwhelmed.
Okay, so that's really interesting. So it's about finding that sweet spot between being all-knowing and actually getting things done.
Exactly.
Right.
That's the challenge.
And I think all these wacky thought experiments that they talk about in here,
Yes.
like the Yale shooting problem.
Right. The hiding turkey scenario.
Right.
All these things.
They're really designed to just push the limits of what we know about logic.
They expose our assumptions about the world.
Exactly.
How we reason about it.
And the Yale shooting problem, it was really such a game changer because it forced everybody to rethink how we represent
action and change in logical systems.
And it led to all these more sophisticated frameworks for reasoning about the world.
Yeah.
So it's not just logic anymore.
Yeah.
It's logic plus insights from causality, from philosophy of mind.
It's really becoming this interdisciplinary endeavor.
Yes, absolutely.
Which is what makes it so exciting. I think you have all these different fields coming together.
So we've talked about all these abstract problems and theoretical frameworks.
Right.
But I want to get into some real-world applications.
Okay.
I mean, what are some concrete examples of how AI researchers are actually using all of this?
Right. Well, one of the most obvious areas is robotics.
Okay.
If you want to build a robot that can actually function in the real world, in a complex environment like a home or a workplace, it needs some kind of common sense.
It can't just be like following a program.
Exactly.
It has to be able to think on its feet.
It needs to be able to adapt to new situations.
So what kind of things are we talking about?
Well, imagine a robot trying to navigate a cluttered room.
Okay.
Or clear a table full of dishes.
Okay.
It needs to understand.
The
properties of the objects.
Yeah.
The relationships between them. The consequences of its action.
It's like it needs to understand physics and spatial awareness.
Exactly.
And even a little bit of social etiquette.
Right. And that's where common sense reasoning comes in.
Yeah.
Researchers are developing formal systems that allow robots to reason about things like causality, spatial relationships, even social norms.
So you're building robots with common sense.
In a way, yes.
That's incredible.
That's pretty amazing.
And we're seeing robots that can, like, assemble furniture, fold laundry.
Assist with surgery, even.
Wow.
It's pretty remarkable.
So this all ties back to John McCarthy's dream of formalizing common sense reasoning.
Right. And the question is, can we actually capture all of common sense in a machine?
Right.
It's a huge concept.
It's a huge question.
Yeah.
It really is. I mean, how do we even begin to think about that?
Well, it's a grand challenge, and it'll probably keep researchers busy for a long time.
Yeah, generations probably.
But even if we don't achieve that ultimate goal, the pursuit of it has already given us some really valuable insights.
Okay, let's go.
Well, it's made us think about knowledge and reasoning and intelligence in a whole new way. What does it really mean to understand something?
Yeah.
What are the basic building blocks of common sense?
Right.
How do we represent those concepts for computers?
So we're not just building AI systems, we're actually using AI to understand our own minds better.
Exactly.
That's pretty profound.
It is.
There's an example in here about the egg cracking problem,
Oh, yes.
which sounds kind of mundane,
Yeah, it's a great example.
but I bet it's not.
It's deceptively simple.
Yeah, tell us about it.
So the problem is this. How do you formalize all the knowledge and reasoning required to describe the act of cracking an egg?
I see.
Sounds simple, right?
Yeah, but you just hit it on the edge of a bowl.
But there's so much more to it.
Right.
You need to understand the properties of eggshells,
Okay.
the force required, the
Mhm.
concept of a container to catch the contents.
So you're basically trying to teach a computer to be a short-order cook.
In a way, yes.
One cracked egg at a time.
It's a microcosm of the bigger challenge of encoding common sense.
Right.
You have to consider how to represent knowledge about physical objects, how to reason about cause and effect, how to plan a sequence of actions to achieve a specific goal.
Right, so it's not just about cracking an egg, it's about understanding all the underlying principles.
Exactly. And amazingly,
Okay.
there are AI systems that can solve this problem, at least in theory.
Wow, really?
Yeah, researchers like Murray Shanahan, Vladimir Lifshitz, Leora Morgenstern, they've developed formal systems, often using something called the situation calculus or the event calculus.
Okay.
And these systems can represent the knowledge needed to crack an egg and even prove that a given plan will work.
So they can write a mathematical proof
In essence, yes.
that shows how to crack an egg.
It's pretty incredible.
It is incredible.
Huh.
But how do we know if these systems are truly demonstrating common sense? Or are they just following a very cleverly designed set of rules?
That's the million-dollar question, isn't it?
Or-
It's something AI researchers debate all the time.
Yeah.
There's no easy answer, but there are some guiding principles.
Okay.
One is to make sure these systems are grounded in real-world data.
Okay.
We can't just rely on our intuitions about common sense. We need to test these systems against the messiness and complexity of the real world.
So it's about running experiments both in the real world and in simulations
Exactly.
to see if the AI can handle the unexpected.
You got it.
Okay, and what's another principle?
Another crucial principle is transparency.
Okay.
We need to be able to explain how our AI systems arrive at their decisions.
So it's not just about getting the right answer.
Right.
It's about understanding the reasoning behind it.
Exactly, and being open to revising our systems when they make mistakes or overlook important factors.
So it's a process of constant learning and refinement.
It is, and it requires a good dose of humility.
It's acknowledging that we don't have all the answers
Right.
and that our AI systems are still a work in progress.
Absolutely, and that's what makes this field so fascinating.
I agree. It's this blend of technical brilliance and philosophical awareness.
It's a beautiful combination.
It is. It really is. Well, it's been an incredible journey exploring the world of logic-based AI with you today.
It has been a pleasure.
We've covered so much ground,
Yes, we have.
from the fundamentals of logic and its role in AI,
To the challenges of formalizing common sense.
and the thought-provoking implications for the future.
And we've seen how AI researchers are drawing inspiration from philosophy
Yes,
to tackle these challenges.
and how the quest for artificial intelligence is ultimately a quest to understand ourselves and the world around us.
A quest that's still unfolding.
And for our listeners who want to delve even deeper into this captivating topic,
Yes.
we've got a treasure trove of links and references in the show notes.
It's an old rabbit hole to explore.
Exactly. Until next time, keep those philosophical gears turning.
And those logic circuits firing.
And who knows, maybe you'll be the one to crack the code of common sense AI.